All of our everyday experiences are closely tied to feedback signals from our surroundings that either promote or discourage our actions in the future. Precisely how we learn from successes and failures can determine the efficiency of this feedback-based learning. A collection of subcortical clusters in the brain, known as the basal ganglia, is thought to be the neuroanatomical location for where these feedback signals are processed. Interactions between cortical areas and the basal ganglia are thought to promote feedback learning. The two main pathways in the basal ganglia that process feedback signals are the direct go pathway that promotes behavior and the indirect no-go pathway that suppresses behavior. Within each pathway, there are neurons with pathway-specific dopamine receptors that activate each pathway. D1 receptor neurons in the go pathway and D2 receptor neurons in the no-go pathway. There is a genetic variant for the dopamine receptor in the D2 no-go pathway that associates with lower levels of available D2 receptor throughout the brain. Thus, carriers of this genetic variant are believed to have a lower sensitivity to negative feedback signals in the D2 pathway, such as the losses that lead to behavior suppression. We hypothesize that the presence of the DRD2 polymorphism interacts with the magnitude of the dopamine response to impact sensitivity to gains and losses during learning. We looked at a sample of 438 neurologically healthy adults who were genotyped for the variant with an insertion or deletion of a cytosine nucleotide in the 141 position, numbered from the 5' end, in the DRD2 gene, referred to as the DRD2 variant. In addition, these participants completed the Iowa gambling task to measure their overall ability to use feedback to effectively make long-term value-based decisions. This task is made up of 4 distinct decks of cards, 2 of which have an overall payoff and 2 of which have an overall loss. Between these 2 pairs of decks, one has a higher frequency of rewards to loss than the other. We are then able to calculate the payoff score, the main task measure, by taking the amounts of selections from the 2 high-paying decks minus the 2 low-paying decks. The sensitivity score, a control measure for the sensitivity to high frequency of rewards, was also similarly calculated. In addition, in the fMRI, participants completed the ventral striatal reactivity task to measure the magnitude of their dopamine response to gains and losses during learning. Here I have plotted the distributions of the measures we used, which are not all uniform, but similar between the carriers and non-carriers. Using linear regression models, we found that the participants with the DRD2 variant or lower ventral striatal reactivity both tend to have lower payoff scores. The scatter plot of ventral striatal reactivity versus payoff seems to imply an interaction between DRD2 variant presence and ventral striatal reactivity on payoff, as seen through a steeper positive slope for the non-carriers and a flatter positive slope for the carriers. However, we did not see a significant interaction between the DRD2 variant and ventral striatal reactivity on payoff. Our control measure, sensitivity, also showed no main effects or interactions. In conclusion, having lower D2 receptor density or a lower reactivity to reward feedback leads to an overall lower ability to perform value-based decision-making. Counter to our primary hypothesis, we did not see an interaction between D2 receptor density and reactivity to reward feedback and the ability to perform value-based decision-making. Therefore, there is inconclusive evidence that lower sensitivity to negative feedback signals in D2 sensitive pathways interacts with reward reactivity to determine the effectiveness of learning during value-based decision-making. A future theoretical direction would be to run simulations of the D1 and D2 pathways in order to test other possible mechanistic roles of the D2 pathways in feedback learning. A future experimental direction would be to use another measure of feedback learning that separates between sensitivity to losses and gains.